Energy change of electron. Energy of photon equal to the energy change equal energy final minus energy initial. The initial energy can be calculated as negative RH times 1 over n square, n initial, the n must be initial, for E final equal negative RH times 1 over n square, and the n must be the n final energy level of the final, the electron at the final energy level. Here electron at initial energy level. So energy change equal energy final minus energy initial. If you substitute energy final minus energy initial from this equation, you have this is the equation for energy initial, this is equation for energy final. So we know that change in energy equal energy final minus energy initial substitutes the energy final minus energy initial, which is our n is final because it's energy final, and this is n initial square is energy initial. If you substitute this, and it will become this one negative will become positive, and this is negative. So negative, if you put it at the back final, if you put it at the back here, negative, and the positive at the front, it will become n initial plus minus n final, because this is negative final, positive initial, so you just change the position. Okay, positive here, positive at the front, and the negative at the back. It will become initial minus final. So that's why if you want to calculate energy change of electron, take out the RH from here, take out both RH, multiply by 1 over n initial square minus 1 over n final square, because positive negative, so negative final. Note that even though E final minus E initial, here final initial, but when you change the signs, when the signs is negative and negative, so positive, and then you change their place, here the n initial at the front because you want to put negative at the back, so that's why it becomes n initial minus n final. Don't be confused with this one. So this is how you get this equation. Energy change equal RH times 1 over n initial square minus 1 over n final square. Okay, the position, you just change the position initial at the front, because initially final at the front, but now initial at the front because you just want to change the positive at the front and negative at the back, so that's why initial minus final. Use this final equation to calculate the energy change of an electron. Energy released or absorbed equal to energy difference between two energy level, energy change or energy difference. So this is the equation that we got from previous slide. N initial square minus n final square, this is the equation that we use to find the energy release or energy absorbed or energy difference or energy change. They are the same thing. Delta E, okay, energy change delta E is also known as energy of a photon. Photon is particle of light. Our RH, Rydberg constant, 2.18 times 10 power of negative 18 joule. This equation, energy of photon delta E, is equal to this. Delta E is also equal to h nu. This is not V, this is nu, the Greek letter. Nu is equal to frequency. We know that frequency is equal to C say a speed of light with a value of 3 times 10 to the power of 8 ms negative 1 over lambda. Lambda is a wavelength, so frequency is c over lambda. Delta E is equal to hc over lambda. Lambda is a wavelength. Differences between ground state and excited state. Ground state is when n equal to 1. Excited state, n equal to any value above 1, any value greater than 1. Ground state is the lowest allowed energy state, it's the closest to the nucleus, electron closest to the nucleus. Excited states is higher energy than the ground state, means it's higher energy than n equal to 1. Ground state is the most stable energy state because it is closest to the nucleus, while excited state is a state or level after an electron absorbs energy, means it's above n equal to 1, so when electron moves above n equal to 1, it absorbs energy. Electron closest to the nucleus makes the energy state more stable, so when electron is further from the nucleus, stability of electron decreases. That's for excited state. Electron transition in hydrogen atom. This electron transition shows that electron falls from n equal to 4, this is n equal to 4, to n equal to 1. When electron is fall from higher energy level to lower energy level, energy released during transition or energy is emitted during the transition. Higher energy level to lower energy level, energy is released. Our n initial is n equal to 4. n equal to 4, n initial. Our n final is n equal to 1. Where n1 is n equal to 4, n2 is n equal to 1. So our n2 is final. n2 and final, okay, n2 and final minus E initial, E1, our initial n equal to 4. So final minus initial. Final n equal to 1, initial n equal to 4. This is our delta E. Delta E is also equal to h nu, h frequency. Next, from n equal to 1 to n equal to 4, from lower energy level to higher energy level, energy is absorbed. Energy is absorbed, so from the ground state is n equal to 1, excited state n equal to 4. This is the most stable because it is the closest to the nucleus. Lower to higher means energy is absorbed. So here, our n final is n equal to 4. Our n initial is n equal to 1. Okay, so delta E equal, you can use this, delta E, or we can use this delta E. But we cannot use h frequency because we don't have the info for frequency here. We only have the information for n. So our n, delta E equal RH times 1 over n1 square, so n1 initial, minus 1 over n2 square final. Initial, final. Because according to the previous slide, delta E equal RH 1 over n initial square minus 1 over n final square. So if we want to calculate for this, our initial is n equal to 1. If you want to calculate for this one, our initial is n equal to 4. You'll get the delta E when you substitute the value of n initial and n final. Example, 1 mole of electrons drop from the 4th energy level to the 3rd energy level. So this is 1 mole, not 1 electron, 1 mole of electron. But for this one, this equation is only for 1 electron, not 1 mole. from the fourth energy level to the third energy level. So from n equal to 4 moves to n equal to 3. Calculate the energy of electron at the fourth energy level. At the fourth En E4, our n is equal to 4 because at the fourth energy level, not the electron transition, just the energy of electron at that particular energy level. So E4 equal negative RH 1 over 4 square, our n equal to 4, so 4 square, negative 2.18 times 10 power of negative 18 joule, that's our Rydberg constant, times by 1 over 4 square, equal negative 1.36 times 10 power of negative 19 joule. This is just the energy for one electron, energy of electron. The energy of the photon emitted from the transition. So from the transition, photon emitted, the keyword emitted, we know that from higher to lower energy level. So that's why it's emitted. If it's from lower to higher, it will be absorbed. So energy emitted makes sense because from higher, fourth energy level to third energy level, so energy emitted. This is electron transition, so we use delta E because the electron changed, the value of n changed, the energy level changed, so we need to use delta E. 1 over n initial square minus 1 over n final square. This is the equation for delta E when the value of n is known. So 1 over 4 square, our initial from fourth energy level, so our initial is n equal to 4, final n equal to 3. Delta E is equal negative 1.06 times 10 power of negative 19 joule. Frequency of this photon, frequency is delta E equal h nu. We already have the value of delta E. This is the value of our delta E. Frequency is nu. H is Planck constant. H is Planck constant 6.6256 times 10 power of negative 34 joule second. So our frequency, the unit is per second. Unit for frequency is per second or hertz. That's a unit for frequency.